Hey there everybody, I'm Chili. Welcome back to 3D Fundamentals Tutorial 3. Today we're talking about 3D rotations. Now 3D rotations are pretty easy to figure out once you have a firm grasp on the 2D rotation transformation. But if you need a refresher course on 2D rotation, I'll put a link on the wiki page to that shit. So the way that site works is basically our retina is a 2D image sensor array. And a 3D world is being projected onto it. So the question there is, well, how do we see 3D then? You know, how can mirrors be real if our eyes aren't real? Well, there are various cues or clues that our brain picks up on to help it build a map of the 3D structure of the world and the objects in the world. One way a brain can be helped to perceive the 3D structure of an object is by presenting it with multiple views or 2D projections of the object from different angles. This helps not only in gaining more structure information, but it also lets you see, parts of the object that would have been obscured at some viewing angles. Like take a look at this 3D model of a protein here. Just looking at it like this, maybe you can get an idea of the shape, but you can't really be sure, can you? Only when you start to rotate it do you understand that, it's longer, it's not a sphere. It's longer than it is round, or whatever you want to call it, and it's got protrusions and shit, but it's only by rotating it that you get an idea of, the full structure. Then your brain can get an idea, it's got like a hole in the middle here and shit like that. So our goal for today is to apply rotation in 3D to our cube so that the wireframe, doesn't look like shit. So let's go back to first principles, the good old 2D rotation. Here it is. You got your matrix representation, and if you multiply that out, you get this formula here. Now, I'm not going to go over why this sine cos bullshit gives us rotation in this video, because, that's a prerequisite of coming to this course. But like I said, I will put a link up to a previous video I did explaining all this bullshit. It's pretty damn good if you ask me. I start off by explaining radians, then I do trig functions, and there's then 3 different derivations of this formula. I know derivations, I have the best derivations. I'll also put up a link to an explanation of encoding transformations with matrix multiplication. Alright, so what does that look like in 2D space? Well, let's go back to our little diagram here with our circles, and we'll assume that the origin is at the center here, and X is going in this direction, and Y is down, because that's how we usually do it in 2D graphics. And if you apply that rotation matrix with a positive theta, what you're going to get is a rotation like this, in this direction here. And that's your good old 2D rotation. There's nothing really much to say about it. It's just rotation, right? But we can say one thing about this rotation is that the direction of the rotation, we're rotating from the x-axis into the y-axis. So rotating x-axis into y. Alright, now like I said before, we can embed 2D space into 3D space, and it works basically the same as it worked before. So what does this rotation look like in 3D space? Well, take a look at this. First of all, let's figure out where our axes are. So this is saying Z is up. So let's agree with that. That means that if we're using our left hand rule, middle finger points up. So our thumb, which is the x-axis, is going to point this way. And our index finger, which is the y-axis, is going to point this way. So, and if you notice, I don't know if you can tell, but 3D Studio Max labels this as the x-axis and this as the y-axis here. And that's because 3D Studio Max uses a right-handed system, but we're using left-handed, so we're going to ignore what 3D Studio Max says and say, this is Z, this is positive X, and this is positive Y. Alright? So, we're rotating from the X-axis into the Y-axis, and that's going to look something like this. And as you can see, it's basically the same idea. There's nothing different than in the 2D system. We're just looking at it at a different perspective now, because 3D Studio Max is rendering this with nice perspective. So we generally call this, when we're rotating in 3D, we call this rotation a rotation around the Z-axis. And it makes sense. If you think about the Z-axis, it's acting like a kind of axle, and everything is rotating around it, right? We say this because, as you can imagine, we can rotate in different ways, not just around the Z-axis. You can also rotate like this, and you can rotate like this. And any other arbitrary axis you want to pick, you can rotate around that. So we have to differentiate between all those different kinds of rotations. So we call this rotation around the Z-axis. And as you can see here, rotation around the z-axis is analogous to rotation in 2D. It does the same thing to the x and y coordinates of all the points that are being rotated. Now, because the same thing is happening in 2D rotation and 3D rotation around z, we can infer that the rotation matrices are also the same. So we can write it like this. Now, obviously, there's one big difference, and that's that we're now working in 3D. So we now have 3 element vectors, and we have to multiply these by our matrices. So when we're multiplying them, the dimensions have to line up. So the matrix has to be 3 by 3. And right now we've only got 2 by 2 elements filled. So what goes into these spots here? That's the question. Well, let's try a little experiment here. We're going to take some of these points or these circles, and we're going to modify their z values. And we're going to see how that will affect their rotation around the z-axis. So we'll just take a few of these guys, we'll just pull them up or down, and then we're going to select the whole damn thing again, and we're going to rotate around z. Now, it's kind of hard to tell with the perspective and anything, but it seems like changing their z has not affected the way the x and y are generated during rotation. We can verify this. We'll give it a big rotation here, and then we're going to look at it back in the 2D view. And as you can see here, they're still organized in neat rows and columns. So we know that changing the z value has nothing to do with rotation around the z-axis. So for example, x prime is equal to x times cos theta minus y times sine theta plus something times z. But we know that z cannot affect the outcome of x, so this must be 0. And the same for y, 0. And there you have it. So we've filled in 2 of those blanks. Let's run another experiment here. So we're going to go back to our 3D viewport here. And the second thing we can ask is, well, how does this rotation around z affect the z coordinates of the values? How does it affect them? Well, let's rotate them around here. And as we rotate around z, we notice that all the points keep the same z coordinate. They keep the same height. All the ones in the plane remain in the plane, and all the ones that we have offset remain at their offsets. So, from this, we can make another inference. Since the z values are just staying the same, we know that x and y input has no effect, and the output is just the same as the input, so it's just z times 1, z prime. So z, for rotation around z, z prime is just equal to z, and that's the matrix. And this is the matrix that you need for rotating around the z-axis. So let's take a look at our code now. If you sync with the remote repo, you'll see this branch, T3-rot3d, and you can check that out. There are 3 changes here, 3 commits, and I've set some local branches for the first 2 commits, but the final code is T3-rot3d, so you can check that out. So I'm going to start here on video 0, where I added the 3D matrices in the test. So let's take a look at the code. So in mate 3, first thing, I added a multiply assign operator for matrix by matrix multiplication. So it just uses the multiply operator to, multiply and assign. Just because I had one for the scalar multiplication, I thought I'd make it symmetrical and add one for the matrix multiplication. Next, rotation Z. Here it is. So you calculate your sine theta, you calculate your cos theta, and then you return a matrix with those values filled in. And you see here, this is exactly what I showed you in the derivation. It's the same thing. So like I said, it's pretty goddamn easy to derive 3D rotation around Z if you already know 2D rotation. Now the question is, how do we derive the rotations around the other axes? Well, check it. Rotation around the y-axis basically looks like this. Alright? And it's basically the same idea. Now it may look a little different, but let me reorient the circles so that they're the same as we had before. Alright, I need to get them... I think that's about right. And now if you see I rotate around the y-axis, it's the same idea, right? We're just rotating these guys around a center point. Now, we could rederive the formula and the matrix from scratch for this new axis of rotation.
Ain't nobody got time for that.
Or we could be smart, recognize that this is the exact same process as rotation around Z, just with the roles of the axes and the dimensions interchanged, and just transform the above matrix with some logic and substitution. So here's our matrix for rotation around Z. That's rotation from the x-axis into the y-axis. Let's derive our matrix for rotation around the y-axis, which is rotating the z-axis into the x-axis. So first things first, let's give the rows and columns of our matrix some labels. So we'll call this x, y, z columns, and the x, y, z rows. Now, like I said, these are basically the same operation, it's just the names of the axes have been changed. So, in this operation, we're rotating around z, and we're rotating x into y. Here, we're rotating around y, and we're rotating z into x. So, here, if we look between these rotations, the axis of rotation has changed from z to y. So let's change what was z in this one to y in here. Now we're rotating from z into x, and here we're rotating from x into y. So here x has become z, and the thing we're rotating into, y, has become x. And we can do the same substitution for the rows. And here we have our renamed matrix, and this will allow us to rotate around the y-axis. The only problem is that this order doesn't work in our system. Our system is ordered x, y, z. So all we have to do now is just reorder the rows and columns. So let's set up a blank 3x3 matrix labeled in the correct order for our system. And now I just got to map these values onto this matrix. So if we start with xx. So what is xx? So we look in our y rotation matrix and we see that that's cos theta, right? So we write cos theta. And then what is xy? Well, that is 0. So we write 0. And xz is negative sine theta. So we go negative sine theta. And the same thing. What's yx? That's 0. What's yz? That's 0. What's yy? That's a 1. And then in here, we're going to have zx is sine theta. And zy is 0. And zz is cos theta. And there you go. You've got your three-dimensional rotation matrix for rotation around the y-axis. And if we look at the code, we see that indeed that is the rotation matrix for rotation around y. And if we use the same method, we can get the rotation around x, and it looks like this. So you can see you've got in the diagonal this way, you've got cos, and that doesn't change. And in the opposite diagonal, you've got sine and sine, but one of them is negative. And so for the z, the negative's on the bottom. For the y, negative's on the top. And for x, is negative's on the bottom. And it's basically the same formation, just, moved around a little bit, which is what you'd expect because generally it's the same operation, just done on different axes. So great. Now we can rotate around, the z, the y, the x-axis. That's sweet. And you might say, well, that's great, Chili, but what if I want to rotate around a different axis? I mean, I can only rotate around 3 axes. That seems very limiting. But you see, the thing is, you can put a 3D object into any kind of orientation simply by combining the rotations of these 3 axes. You can generate, or you can move it into any orientation possible by just combining 3 rotations together. So now it's time to test out our rotation matrices. And if you go to game.h, you'll see I've added 3 variables here, member variables, theta, x, y, and z. So that is the angle of rotation around these 3 axes, and d theta is just the speed of rotation basically. And if you go into update model now, I'm checking the Q, W, E, ASD keys, and these are going to control the angle of rotation, right? QWE is going to increase angles of rotation, ASD is going to decrease them. And here's where the work is done in compose frame. So as usual, we get our indexed vectors for the lines, and here's where we build our rotation matrix. So we generate rotation for X, Y, and Z. We concatenate those matrices to generate our rotation transformation. Then for each vertex, for our lines, first we transform them by rotating them around the origin. Then we move them in the Z, and then we transform them to screen space. And then as usual, we draw them like this. So if we run the program, we get our, our square as usual. But if we press the Q, W, E keys, now we can rotate it. So here's rotation around the Z axis, and here is rotation around the Y axis, and here's around the X. And you can see now, as we rotate it, you can see that it is a 3D cube. Now, one thing I'd like to draw your attention to is there is a bit of aliasing or ambiguity going on with this rendering. So we can actually see 2 different rotations here. Let me just try to get a good one. All right, this is pretty good. So I can see 2 different rotations here. I can either see it rotating, this is the front face, and it's rotating around like this. But I can also make my brain think that this is the front face or the top, and it's rotating around like this. Can you see both? Wait, let me see if I can get the other one again. It's either rotating. I can only get the one where the top is facing us. I think I see it now. This way, right? Yeah, I got it. So our brain is actually, my brain is flipping between 2 interpretations of this. It's quite interesting. And basically it has to do with the way we are projecting this. But that is going to be covered in the next lesson, so don't worry about it right now. Now there's one more thing I want to show you guys. So if you look at here the history for the commits, this commit here is video 1 on my system, so I'm just going to switch to it right now. You guys don't have this branch, but you can create it if you want. So by right clicking and going, new branch. So here I've changed the code a little bit for generating the rotation matrix. I've got now a ternary operator here being controlled by the control key. So if control is not being pressed, we generate rotation X, Y, and Z and concatenate them. But if control is being pressed, I change the order of the matrices. I change the order of the concatenation. So now it's Y, Z, X. And this will actually change the orientation of the cube. So let's run this for a second. And let's add some Z rotation and some Y rotation and some X rotation. So here we have our box rotated around the 3 axes. And if I press Control, you see we get a completely different orientation. So the rotation transformation is not commutative. I forget the word, but anyways, what it means is that if you switch the order, you will get a different orientation. So you've got to be careful of that. Now, as long as you be consistent and you always use the same order, then everything should be fine. But just be aware that the order of rotation matters. You can't just switch it up in any way you want. So for example, in the DirectX math library, you've got a function here called XM matrix rotation roll pitch yaw. And you specify these 3 values, the roll, the pitch, and the yaw, which is pitch is X, yaw is Y, and roll is Z, apparently. And it returns a rotation matrix, so it basically returns the concatenation of the 3 matrices I showed you. And yeah, and it says here that the order is roll first, then pitch, then yaw. So as you can see here, they specify this in the remarks because it's important the order in which they're applied. It's important to know this stuff. Now you might ask, well, how can we tell what direction a rotation is going to be around an axis? And the answer is there's a left-hand rule for rotation. So we're back in the realm of hand jobs. So check out this image here. Very suggestive. And this is how you tell what the direction of rotation is going to be. So you see this is a left hand, and you make like you're going to, jerk someone off, but you stick your thumb out. So the thumb is going to point in the direction of the axis. So if you're doing a rotation around the x-axis, your thumb is going to point in this direction, the positive x direction. And the curl of your fingers moving from your wrist to the tips, that shows the direction of rotation. And that works for any axis. So if you look back on our diagram here, the z-axis is pointing out. You point your finger out along that z-axis and you see that your curl is going to be going around this way. So from x into y. And same thing, if you point your thumb up on the y-axis, you see that the curl is going from the z to the x. So it's very easy. It's a left-hand rule. Just jerk that axis off. Now the last thing I want to talk about here before we finish up today is angles. So we're working in radians, right? So here's 0 radians. Here's pi. This could be pi over 2, and this could be 3 pi over 2. So going along from there. Now I say this could be 3 pi over 2. This could be 0. Holy shit, the world could be ending right now, judging from the sounds outside my window. But anyways, this could be 0. This could also be 2 pi. This could also be 4 pi, right? 2 pi meaning go twice around the circle. Because angles, radians or degrees or whatever you want, they're periodic. So 0 is the same as 2 pi, is the same as negative 2 pi, and so on and so forth. So that's why rotation is a periodic phenomenon. And as you see here, we can just continually add angles to these theta values and they will just continue to rotate. No problem, except there is a problem because these are floating point numbers, right? And as floating point numbers get very large, they lose precision in a sense. Because think about it. Floating point number is a number like, for example, let's say, 3.14159, right? Times 10 to the 0. Now, as this number gets larger, as we increase it by a lot, let's say it becomes, 3,000-ish. Now, before our precision was down to the 10th, 100th, 1000th, 10,000, 100,000th place. But as it gets larger, we lose precision in a sense. And that's not a good thing. And we don't need to store large angles because, as we can see here, 0 is, for example, the same as 4 pi is the same as 4 million pi. So what we want to do is we want to keep our angles within a 2 pi range so that we don't lose precision like this. And it doesn't really matter what 2 pi range you choose, but I'm just going to choose between negative pi to positive pi. And the way we do that, it's quite simple. So I'm going to change to this branch. This is the final branch here in the code. And if I go to ChiliMath, I've added a function here. It's just a templated function, so it works for float and double. I've also added a constant pi for a double pi. And all you do here is you take the modulus, or the modulo. So we mod by 2 pi. So basically what this is saying is, let's say we input the value 3 pi. This is just going to output pi, right? Or if we do 5 pi, it's going to output pi. If we do 6 pi, it's going to output 0, I believe. So modding it by 2 pi will bring it into the region of 0 to 2 pi. But we want a region of negative pi to positive pi. So after that, if we're greater than pi, then we subtract 2 pi from that. And that'll bring us into the region of negative pi to positive pi. And then in the code here, where is it? Game.cpp, we just add the d theta times dt, which is the time step. And I've just clamped the time step down to 1/60th. So it'll run faster for people with, higher refresh rates than me, but it doesn't matter. It's not important. So we add the change in theta to the theta, and then we wrap the angle to the pi to negative pi range. And we do that for all these things here. And the rest is the same. I removed that ternary operator back to our standard code, and that's it. There you have it. And there is 3D rotation for you in action. It's pretty sweet if I do say so myself. And that's it for today's episode. Next time, we are going to do something that will say, add a little perspective to the situation. But for now, I'm Chili. This was 3D Fundamentals. If you liked the video, please click the like button. It helps a lot. And I will see you soon with some more 3D awesomeness.